This video is going to be about radicals and their reactions. We will talk about what a radical actually is, we'll talk about some of the reactions that happen, the general mechanism for it, and also an example using CFCs and ozone. First of all, what is a radical? A radical is an atom or molecule that has an unpaired electron. This makes them very, very reactive in most cases, because as you may know, molecules tend to pair up to have a full shell of electrons on their outer shell. So we take something like sodium chloride, Na+, Cl-, the chlorine will gain an electron to have a full outer shell, and the sodium will lose one, so its outer shell is full as well. We may have a covalent molecule or diatomic molecule, such as Cl2, where the outer electrons are being shared, so they both have a full shell. So we look at a chlorine radical, so I've used chlorine in these examples. The outer shell has 7 electrons represented by these dots. It has space for an 8th one around here. However, it doesn't have that unless it reacts with something in a covalent or ionic way. We look at the electron structure of chlorine. It's 1s2, 2s2, 2p6, 3s2, 3p5. Now if we just look at the outer shell, which is the n=3 shell, we've got the s has 2 electrons, so that's the s orbital, these are the p orbitals. Then this has 5, so 1, 2, 3. If you remember how to fill up electrons for one of my previous videos, we don't pair them up until we can no longer put them in single subshells and orbitals for 5. So that's the electron structure. Now, as you can see, it has space for an electron here, so we have an unpaired electron, making it very, very reactive. Now, should we look at some of the reactions that can occur, the general mechanism, as I like to call it? Well, we have initiation to create a radical. This usually involves UV radiation that breaks bonds. So if we had the diatomic molecule Cl2, now UV can come in and actually excite this bond. As you may know, bonds vibrate, they're not still. They vibrate back and forth all the time. And if you put in too much energy, these bonds can break. And when we have a diatomic chlorine molecule and we pump a lot of UV radiation into it, it actually breaks through homolytic fission, meaning one electron goes to one atom and one electron goes to the other, which forms 2 radicals. How we represent a radical is with this dot. This dot next to the molecule represents as an unpaired electron. It is a radical. So that's the initiation. What happens then after the radicals are formed is a process called propagation. Now this is where the radicals go on to react with other molecules or atoms in the air, forming a product and another radical. And you'll see an example of this in the next slide where I'm talking about CFCs and ozone. After that, after the propagation step has occurred, at some point there will be a termination step. This is where radicals come together and react together, such as 2 chlorine radicals. They can come together and form a stable molecule that isn't a radical anymore, as this bond could reform, for example, like this. And that's how these processes of radical reactions end. Let's look at a quick example of this. CFCs, or chlorofluorocarbons, and the reaction with ozone. We have the CFC, CF2Cl2, and once we put UV into this, it can actually split the chlorine-chlorine bond. And this step is known as the initiation step, as discussed previously, as radicals are being formed. Now what can happen then is these radicals can go and react with ozone. And if you didn't know, ozone is very, very good because it shields us from some of the harmful radiation coming from the sun. So only a certain percentage of UV gets through to us, which causes burns and skin cancer, because ozone blocks a lot of this out, especially the higher energy versions, which causes more damage, as there's something called UVA, UVB, and UVC, and it blocks some of them out and allows some through, and some are more damaging than others. So here we have a chlorine radical reacts with ozone, which is denoted by O3, forms another radical and a product, which is oxygen in this case. That radical product there can react with an oxygen atom in the atmosphere to form a chlorine radical and oxygen once again. So as you can see, the reaction is O3 plus an oxygen atom goes to 2O2 would be the overall bit of that, as that molecule would cancel and those molecules would cancel. As you can see, that's basically the destruction of ozone, which is very, very bad for human beings. And this process is the propagation step, because the radicals are reacting with molecules to form a product and more radicals. Now this will continue to happen indefinitely until all the radicals are used up. And there are several different termination steps. I'm just going to choose one example here. So the two chlorine radicals that are being used throughout, that were created up here, could react together to form Cl2, and that's your termination step. You could also have CF2Cl radical, two of them could go and combine, become CF2Cl, and then they can bond. If the radical's on carbon, we could have another carbon and then two fluorines and a chlorine on there, depending where the radical is in the molecule. And basically there are a huge number of termination steps, because any radicals from any step of the process can react together. So we could have ClO and Cl react together, these two could react together and things like that. There are several different ways that this could end. Now CFCs are particularly bad when we study this, is because fridges and freezers from a long time ago contain CFCs in their sort of cooling fluid as such in the back of them, so they'll just be put in landfill and incorrectly disposed of, and this would just leak into the atmosphere and damage ozone. And there was a massive hole on one of the poles at Earth, and yeah, very, very bad for all human beings. That completes the video on radical reactions today. I hope this has helped. It was a very short one, as you don't need to know too much, but the main things you remember are the initiation, propagation and termination steps, as you can apply this to any reaction involving radicals that you come across. Thank you for watching.